So for medium carbon, this will be ranging from 0.3 to 0.5%, where for high carbon, this will be ranging from zero point 0.5 to close to 1%, right? Is welding of high carbon steel is difficult or this is simple compared to low carbon steel? So if you're thinking welding of high carbon steel, that is much more difficult than welding low carbon steel because of greater tendency of martensite formation in your heat affected zone, right? So you're talking about this light etching ferrite and dark etching pearlite. Let's say your base metal is having some ferrite pearlite colony, you know. Now we are talking about now much higher carbon percent. So volume fraction of perlite will be significantly higher in the case of medium or high carbon steel compared to low carbon steel. But in the similar way, there will be these three regions: partially grain defined region, and grain coarsening region. Now, in the grain coarsening region, the position D we are talking about, position D we are talking about for grain coarsening region, both high cooling rate and large grain size that will promote the formation of martensite. Large cooling rate and large grain size promote martensite formation. Okay, so if you see the microstructure, uh, I cannot draw the microstructure over here. Anyhow, if you see the microstructure, that will be essentially martensite uh with some amount of uh, benite may form and some nodules of pearlite may form. Right now, in the grain refining region, the position C, in the grain refining region, the lower cooling rate and smaller grain size that will encourage me to form perlite and ferrite. So in the grain refined region, there will be lower cooling rate and smaller grain size. Flux inclusion tendency inside weld metal for fusion welding process, that mainly depends on what? So yeah, means if you are asking of flux inclusion, so always flux inclusion will be correlated with affinity with these atmospheric gases, right? None of the other choices are related to this flux inclusion tendency. What next? Next is steel weldability of thin section depends on, of course, mechanical property, yes, chemical composition also, yes, heat treatment also depends on. So all of these is my correct option. Okay, so we'll be talking about this uh, corrosion resistance maybe in some time, if we get some time. Okay, fine. Next, let us go to this different kinds of cracking tendency. What happen in steel makers, right? So So the cooling rate that will be experienced by your weld metal, your heat affected zone during welding, uh, if if it exceeds the critical cooling rate, that will increase the chance of martensitic transformation. That we know, right? So that is well known from physical metallurgy of the steels. Uh, that this transformation increases the hardness and brittleness, and that generates some tensile residual stress in your structure, right? So that make your steel which will be prone to cracking. So there is something called cold cracking or hydrogen cracking. Okay, so we'll talk about this hydrogen cracking. This is also known as cold cracking. So what is the origin of this? So origin of this problem lies uh, if you have variation in your solubility of hydrogen in steel with temperature. Because of variation in solubility of hydrogen, there will be this generation of this cracking tendency. That is the origin, right? If you are having variation in hydrogen. Now, reduction in temperature that decreases solubility of hydrogen in solid state, and because there will be change in crystal structure. There will be change in crystal structure, and because of that, if you are reducing your temperature, that will decrease your solubility of hydrogen. So, high temperature transformation. So, what are some high temperature transformation in steel? So, we call it high temperature transformation. Austenite, gamma austenite to pearlite or benite. These are called high temperature transformation. So if you are having high temperature transformation, that will allow you to escape some of your excess hydrogen, right? Beyond your solubility limit by diffusion, it will escape. But in the case of low temperature transformation, in case of low temperature transformation. So what is the example of low temperature transformation? This is the example of low temperature transformation. So low temperature transformation is austenite to martensite. That is a low temperature transformation, है ना? So their rate of diffusion reduces significantly, and your hydrogen cannot escape over there, and that is trapped within your steel as solid solution, right? So dissolved hydrogen has more damaging effect in the presence of martensite. So if you have martensite in your structure and hydrogen dissolved in your structure, that is having very dangerous effect in your steel structure, right? So hydrogen dissolved in atomic scale at low temperature, that 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 tends to diffuse out gradually towards some other vacancies. So at those locations where there will be this diffusion of hydrogen, so atomic hydrogen that will convert into some diatomic hydrogen gas, and with time, with continued diffusion of hydrogen towards this discontinuities, as these gases starts to build up pressure in the cavity, and if the pressure exceeds your fracture stress of the metal, wherever there is wherever there are those cavities, after some time the pressure exceeds the fracture stress, right? So my atomic hydrogen, so initially I'll be starting from atomic hydrogen. Then it converts to diatomic hydrogen gas. So it converts to hydrogen gas. And with time, with continued diffusion of hydrogen towards those cavities, the gas starts to build up pressure. So my pressure starts to build up. And whenever it exceeds the fracture stress of uh, those cavities expands by cracking, right? So cracking of your metal that increases the volume, which in turn reduces the pressure. So that's how it will equilibrate. The pressure will equilibrate, right? Fine, fine. So, so this type of cracking and fracture, it takes place after some period of time after welding, right? This is also called delayed cracking. So hydrogen cracking is also called hydrogen cracking is also called delayed cracking. So delay for complete fracture, that depends on what factors. So if you are having delay in your fracture, that will depend on different kinds of factors, which are you have hardenability of steel. So one is hardenability of steel, then amount of hydrogen that will be dissolved in atomic scale, amount of hydrogen that will be dissolved. What else? Residual stress also. So the magnitude of your residual stress that will also affect the delay in your cracking period. So hardenability of steel will affect your critical cooling rate, right? So steel of high hardenability that will promote the martensitic transformation. So therefore it has high hardness and brittleness. So high hardness will increase the cracking tendency, as simple as that. Whereas if you have soft and ductile metal, that will reduce it, right? Now, larger will be the amount of dissolved hydrogen, faster will be the hydrogen induced cracking, right? So larger dissolved hydrogen, cracking tendency increases. So what can be few remedies for hydrogen cracking? We have talked about the reasons for which hydrogen cracking happen. What can be some remedies? So we have to basically control our welding parameters, right? So in terms of controlling of welding parameters, what are they? So we'll be talking about, sorry, for some reason again, the video is not recording properly. Anyhow, so there will be gap in between. There will be some time lag, right? Uh, yeah. Anyhow, I'll be sharing the complete presentation also. So we are talking about these remedies for avoiding this hydrogen cracking tendency. What can be those? So there is this preheating, of course. Preheating. Whenever you are doing preheating and interpass temperatures, control of interpass temperature, that can help to reduce hydrogen cracking, right? So yeah, and post weld heating also. The post weld heat treatment also can be used to stress relieve the weld before it cools down to room temperature. You can stress relieve by doing some post weld heat treatment, right? Now, the stress relief heat treatment cannot be carried out immediately upon completion of welding. The completed weldment can be held at a proper temperature to allow your austenite to transform into a less susceptible microstructure than martensite, right? And then your post-weld heat treatment should be done. So that can also help hydrogen to diffuse out of your workpiece. So those things are there. And then the common sense is if you are using proper welding process and proper welding materials, so the use of lower hydrogen welding process. So we'll have gas tungsten arc welding, gas metal arc welding instead of submerged arc, or yeah. So instead of submerged arc, if you're using those welding techniques of GTW or GMAW, or if you're using consumable, what kind of consumables? So if you are using basic electrodes rather than cellulosic shielded metal arc welding electrodes, that will be reducing your amount of hydrogen present in your welding zone, right? Then you can use your lower strength filler metal also. So I should note it down. I should note it down. I should note it down. So one is this low hydrogen process and consumables. Second is lower strength filler metal. So if you are using lower strength filler metal than the base metal, that can help to reduce your stress levels in the heat affected zone, and that can also reduce the chance of hydrogen cracking, right? So lower strength filler metal, these are there. Okay. The next I'll be talking about reheat cracking. Any question till now? Okay, so if you have no question, we'll be talking on this reheat cracking. Okay, so that is also a well recognized problem in your low alloy ferrite steel that will contain chromium, molybdenum, vanadium, tungsten to enhance corrosion resistance and uh, elevated temperature strength, right? So, yeah, so low alloy ferritic steel, low alloy ferritic steel. In general, reheat cracking is observed over there, and this alloy steel sometimes also called creep resistant ferritic steel. Okay, so creep creep resistant creep resistant ferritic steel. Now, these creep resistant ferritic steels are reheated often to about some 550 or 550 to 650 degrees C within that range, right? After welding to relieve stresses and uh, that can reduce the susceptibility to hydrogen cracking or stress corrosion cracking. Okay. Now, there is some empirical formula. If you remember, we once discussed about those empirical formula uh, in your weldability structure. So here also there is this empirical formula which was uh, which was developed by researcher. So if you if you see this empirical formula, I want to write it down over here. That minus 2. Now when this value of crack susceptibility is equal to or greater than 0, the steel may be susceptible to reheat cracking, right? Now what is the reason of this reheat cracking? So during welding, the heat affected zone which will be near your fusion line, that is heated to temperature very high in your austenitic phase field, right? Where there is this pre-existing carbides of chromium, monel, vanadium, those will dissolve at those high temperatures, right? And austenite grains will grow with time. And then when you will do this rapid cooling, so subsequent rapid cooling, it will not allow you enough time for carbides to reprecipitate, right? Now, if it is not allowing time for carbides to reprecipitate, what will happen? That will result in supersaturation of these alloying elements, right? You got it? So initially it was getting dissolved at high temperature, and then when you are cooling, it is not allowing enough time for carbides to reprecipitate, and it is resulting in supersaturation of these alloying elements as the austenite transform into martensite if hardenability is sufficient, right? Now, when the coarse-grained heat-affected zone is reheated to elevated temperature for stress relieving, so these fine carbides precipitate at dislocations in the prior austenite grain interiors. Okay. Uh, this is a bit confusing, but means I cannot write down everything over here. But what I can do is, what I can do is, there will be this pre-existing carbides, right? I have my chromium, monel, vanadium. All those pre-existing carbides will be dissolved. They will be dissolved, right? And when you are doing rapid cooling, they cannot reprecipitate. because they are not getting time to reprecipitate those carbides. And because they are not going to reprecipitate, there will be supersaturation of those alloying elements. Supersaturation. When gamma austenite transform to martensite, right? Now this coarse grained heat affected zone, when it will be reheated to elevated temperature for stress relieving, those fine carbide precipitate at dislocations. So while you will be doing reheating, fine carbides precipitate, right, in the prior austenite grain interiors, and that will strengthen them before stresses are relieved, right? Now, since the grain interiors are strengthened more than the grain boundaries, and since this occurs before stresses are relieved, crack may occur along the grain boundaries. That is called reheat cracking. Okay. Now, what can be remedies? Remedies for reheat cracking. Remedies. What? What can be remedies for reheat cracking? So, multiple pass welding has been reported to reduce reheat cracking in your creep resistance ferritic steels, right? So, that has already been reported. If you do multi-pass welding process, multi-pass, this is one option. Yeah. Then there is this cracking called lamellar tearing. So, what are the causes of lamellar tearing? Now, in brief, it is the combination of high localized stress due to weld contraction and low ductility of base metal in its true thickness direction, right? If you're having presence of this elongated stringers of non-metallic inclusion, and those are parallel to your rolling direction, you will have those. So this is combination of high localized stress due to weld contraction and low ductility of base metal in to in through thickness direction. So as I was saying, if you have this presence of some kind of elongated stringes of non-metallic inclusion parallel to its rolling direction, so tearing may be triggered by decohesion of such non-metallic inclusion. So usually those non-metallic inclusions are silicates or sulfides, right? Uh, yeah, so that is there. And one of the practical way of avoiding lamellar tearing is to if you employ your joint design that will allow the contraction stress to act more in the rolling direction of the susceptible material and less in the transverse direction. That is a practical way by designing your joint in such a way that you can avoid the lamellar tearing over there, right? Okay, so let's move to the question then. Uh, yeah, yeah. Go through the question once before I read it again. So in fourth question, it states that if you're having reduction in corrosion resistance because of chromium carbide formation at the fusion boundary of austenitic ferritic steel joint. Okay, fine. I will come to that part of this corrosion resistance because we have not discussed it till now. Uh, yeah, fine. Let's go to question 5. So I ask about intermetallic compound formation during welding of steel. If you are having intermetallic compound formation during welding of steel, what are those? So of course, solidification cracking and liquefaction cracking nowhere is not related with formation of intermetallic compound. In reheat cracking, I talked about those carbide precipitation, right? So fine carbide precipitation. It can precipitate into the interior of the grains rather than in the grain boundaries. So they tries to strengthen the interior of the grains, and it may happen because of that fracture initiate along the grain boundaries, right? So reheat cracking is the correct answer. So intermetallic compound formation during welding of steel that will be resulting in reheat cracking. Okay. The next question. Viscous slag formation tendency on the top layer of the molten metal can be eliminated by shielding of molten metal, yes. Whirlpool flowability, also yes. Addition of deoxidizer, that is also true. So D is my correct option, right? I believe there should not be any confusion over here. Then I ask lamellar tearing. So just now I talked about this lamellar tearing in steel element that can be minimized by I talked about this favorable joint design if you are allowing joint design in such a way that your residual stress, the contraction will be in the rolling direction rather than in the transverse direction. That will be minimize your lamellar tearing. Along with that, also preheat and low yield strength filler metal that will also work in your favor to reduce the lamellar tearing, right? So all of these are true. Now, as carbon equivalent increases in the weldment, underbid crack sensitivity. So any kind of crack sensitivity, let's talk about crack sensitivity. If you're having carbon equivalent that is getting increased in your weldment, that is always going to increase, right? That is always going to increase. Next, slower heating rate and longer retention time above upper critical temperature. So if I having slower heating rate and longer retention time, so the time is large enough to grow the grain structures, right? So that will increase the grain growth. These all have been discussed in this session. That will always increase the grain growth if your time is high enough. And then the partial grain refining region. So we talked about this location B, right? Location B in your structure over here. This one. Location B is your partial grain refined region. So the partially grain refining region is subjected to a peak temperature. Which one? Just above the lower critical, just above the upper critical, just below the lower critical, just below the upper critical. So over there, the region is subjected to a peak temperature just above the lower critical temperature, AC1, right? So these all have been discussed. Now we'll move to these corrosion resistant materials. So can we name a corrosion resistant material in steel? So stainless steels are widely used in various industries because of their resistance to corrosion. Okay. So yeah. Home new slide. Stainless steel is corrosion resistant steel. Just wait for some time. Yeah. Yeah. Sorry for the delay. So we'll be talking on the on this corrosion resistant stainless steel. Now the welding of stainless steel, especially the austenitic graded stainless steel, uh, that is important in energy related systems, right? For instance, you have power generation, petrochemical refining systems, all over there. This corrosion resistant stainless steels are used uh, as the main structural component, right? Now, whatever I will be talking right now, that will be focusing more on your heat affected zone phenomena, right? Whatever will be happening in your heat affected zone of welding in stainless steel. Now, stainless steels can be classified. Stainless steel can be classified. So these are Fe based alloy, right? Stainless steel. This is Fe based alloy, right? Now they usually contain this chromium and manganese by weight with addition of nickel also. So there will be this 12 to 27%. This I have taken from online from Google. The composition of stainless steel, it may contain 12 to 27% chromium and 1 to 2% manganese by weight. Okay, 1 to 2% manganese by weight. That you remember. This is the weight percentage. There can be some addition of nickel also. There can be some addition of nickel also. And small amount of carbon is also present. So that can be either deliberately added or as an unavoidable impurity, right? Now, in terms of classification of stainless steel, first we'll be talking of on ferritic stainless steel. Now, this ferritic stainless steel are composed of BCC phase. Okay, this is composed of BCC phase. So, chromium tends to stabilize alpha Fe, which is BCC to be particular, and its high temperature counterpart. What is its high temperature counterpart? That is delta Fe. Okay, so chromium, which is BCC structure, stabilizes alpha Fe into delta Fe. All are BCC in nature, right? And they merge to form the so-called closed gamma loop, right? So, yeah, means if you see this phase diagram for iron chromium, we'll understand that what is this I'm talking about in terms of alpha, delta, and gamma. So let's not again going into direction of iron chromium phase diagram, that also I need to refer. Anyhow, so this alpha ferrite and delta ferrite, they merge to form the gamma loop. Okay, so that will happen there. Now, this ferritic stainless steels have uh, the characteristics of this ferritic stainless steels. Those are similar to those of iron chromium alloy. Okay, that will contain uh, more than 12% chromium to remain outside this gamma loop. Now, to avoid forming an excessive amount of uh, brittle sigma phase, so I should have drawn the iron chromium phase diagram, but please refer from anywhere in from your book or anywhere if you are getting any source of online source of this iron chromium phase diagram, you should refer that first. Iron chromium phase diagram, then you can correlate with what I am talking right now. Okay, iron chromium phase diagram, please refer to that. So yeah, so the sigma phase in iron chromium phase diagram, sigma phase is very brittle in nature. Okay, so to avoid forming an excessive amount of those sigma phase, uh, the maximum chromium content of ferritic SS is generally kept below 27%. So chromium content is kept below 27%, right? And then you have your martensitic gases. Now, martensitic stainless steel can be said to behave like iron chromium alloys containing less than 12% chromium. If it is containing less than 12% chromium uh, inside the gamma loop, then we can say that the characteristics is somewhere similar to martensitic stainless steel, right? Now these alloys solidify as delta ferrite transform to austenite during cooling. So whenever you will transform your delta ferrite structure to austenite, austenitic stainless steel. What is austenitic stainless steel? So if you add nickel, FCC nickel, nickel is FCC structure, okay? If you add nickel into iron chromium alloy, that will tend to widen the range over which austenite will exist, and it will increase its stability at low temperature. So nickel addition work in that way. Now austenitic stainless steel contain at least 15% chromium and enough nickel to maintain a stable austenitic structure over the temperature range, right? Uh, so yeah, that is there. At least 15% chromium addition is there, right? Now, uh, there are a lot many more things in. We do not have much time over here to discuss those things. Uh, so what I can do is, I can write down, I can write down, or I can note down the problems associated with different kinds of stainless steel and their what are their solutions in a gist. Okay, so that I can do. So I'll do that in terms of a table. So this is type of SS. I'll be using smaller font. Okay. So first we'll be talking on this austenitic stainless steel. So the typical problems associated with austenitic stainless steel is solidification, cracking, and hot cracking in partially melted zone. What can be some solutions? We can use proper filler wax, right? Use proper filler wax. Use low carbon grades of SS. You can do post-weld heat treatment to dissolve the carbides. So dissolve the carbides. Okay. Next, for ferritic ferritic stainless steel, this is having low toughness due to heat affected zone grain growth and grain boundary martensite formation. Right? What is the solution? Use low heat input or add carbide and nitride formers to suppress the grain growth. Right? To suppress the grain growth. You can add Ti, titanium or niobium to reduce formation of martensite. Okay, so next we'll be talking with martensitic stainless steel. And what are the solutions? Preheat or post heat treatment, or you can use low hydrogen or austenitic stainless steel. Right? So I have kept it very brief. So let's not go into much detail of those physical metallurgy again. So I have kept it brief to understand what will be the typical problems associated with different kinds of stainless steels and what can be the solutions to uh, avoid those. Uh, we had done so reduction in corrosion resistance because of chromium carbide formation at the fusion boundary of austenitic ferritic stainless steel joint is due to carbide migration. Okay, so B is true. Draw. Okay, so fine. If you have any question, you can ask, or else we will finish today's session over here. Um, Possibly the next session I want to conduct it on next Friday. So the NPTEL team will be announcing it quickly. Uh, because next week I will be out of station. So fine. Okay. Do you have any question? If no, we'll be stopping it over here. Okay. Bye bye.